In this lecture series, we'll learn about the two main mechanisms or pathways of elimination reactions and the reaction parameters that distinguish between them. We've already seen elimination reactions when we learned about the basic classes of organic reactions. So what we'll see now are the two more detailed mechanistic pathways. Remember that an elimination reaction is one that follows the pattern A goes to B plus C. And more specifically, the elimination reactions that we're looking at here are reactions of alkyl halides that eliminate acid to form alkenes. And typically, these reactions require two things. First, they require a base to deprotonate the hydrogen adjacent to the leaving group, or the halide. Second, they require a hydrogen that is beta 2, or on the carbon next to the leaving group. In these reactions, the base deprotonates this beta hydrogen. The electrons in the carbon-hydrogen bond move to form the new pi bond, and the leaving group leaves. These reactions can be categorized into two different classes, E2 and E1 pathways. And as we saw for substitution reactions, these two pathways differ in their mechanistic steps and their intermediates. In an E2 reaction, an elimination bimolecular, the three steps happen at the same time. In an E1 reaction, an elimination unimolecular, the leaving group leaves first, and then in a second step, the base deprotonates the hydrogen adjacent to the resulting carbocation. We'll look at both of these reactions in more detail now, starting with the E2 reactions. The E2 reaction is a bimolecular reaction. Remember that a bimolecular reaction is one that has two molecules in the rate determining step. And here that will be the base and the alkyl halide. And similar to SN2 reactions, E2 reactions will proceed through a single step that includes all of the bond breaking and forming. The reaction begins with the base deprotonating the beta hydrogen. As that happens, the electrons in the carbon-hydrogen bond move to form the new carbon-carbon pi bond. And at the same time, the leaving group, here the bromide, leaves. There are no intermediates in this reaction, and everything happens in a single concerted step. That means that the rate of the reaction depends on the concentrations of both the alkyl halide and the base. And because the base initiates the reaction, it means that these E2 reactions usually require a strong base. Finally, because everything happens in a single step, there are some requirements of how the substrate must be oriented in order for the bond breaking and forming steps to happen at the same time. E2 reactions require what we call an anti-paraplanar arrangement of the hydrogen and the leaving group. And an anti-paraplanar geometry is one in which the hydrogen and the leaving group are oriented in the same plane. And when they're in the same plane, the hydrogen and the leaving group are on opposite sides of the molecule in a trans-like geometry. In the syn periplanar geometry shown on the left, the hydrogen and bromine are in the same plane, but they're on the same side of the structure, or in a cis-like orientation. And an E2 elimination cannot occur from this geometry. Instead, an E2 elimination requires the anti-paraplanar orientation that's shown on the right. Again, in the anti-paraplanar orientation, the hydrogen and the leaving group, here the bromine, are in the same plane and on opposite sides of the structure. This planar geometry is required for the interacting orbitals to align. And the anti-paraplanar arrangement is most favorable because it places the hydrogen and the bromine, or the leaving group, in a staggered conformation, which we can most easily see using a Newman projection. Elimination from this anti-paraplanar geometry is important because it provides a single stereoisomer of the alkene product when chiral starting materials are involved. And I've just indicated that here using our generic structure by numbering the positions to indicate the stereoisomer that will form. E2 reactions also show regioselectivity. In cases where there are two different beta hydrogens that would result in the formation of two different alkene products, like the example shown here, the reaction will favor the formation of the internal alkene, or the more substituted or more stable alkene. And this is known as Zaitsev's rule. The more substituted product is often referred to as the Zaitsev product. In contrast, if we wanted to make the less substituted alkene product, we can do that using a very bulky base. A very bulky base cannot so easily deprotonate the beta hydrogen in the more substituted position, and instead will favor deprotonation of the less hindered beta hydrogen. Here, the one in blue. And this will lead to preferential formation of the less substituted alkene product. This product, formed with the use of a bulky base, is often called the Hofmann product. Now we'll look at E1 reactions. An E1 reaction proceeds through two distinct reaction steps with the formation of a carbocation intermediate. An E1 reaction begins with the loss of the leaving group. And if you remember, this step is exactly the same as the first step of an SN1 reaction. They both start with the leaving group leaving to form a carbocation intermediate. From here, the reaction pathway differs. Instead of undergoing attack by a nucleophile, in the E1 reaction, the beta hydrogen will be deprotonated to form the alkene product. And so E1 and SN1 reactions look very similar, but they differ in what happens to the carbocation intermediate. And that means that for an SN1 reaction, we need a nucleophile, while for an E1 reaction, we need a good base. Finally, because the slow step of the reaction is formation of the carbocation intermediate, the base does not factor into the overall rate of the reaction. And that means that the strength of the base is not important here. Also remember that because we form carbocations as intermediates, carbocation rearrangements can occur during these reactions. The regiochemistry and stereochemistry in these reactions is more straightforward than in an E2 reaction because they proceed through carbocation intermediates. Because there is no geometric requirement for an E1 elimination, like there is in an E2 elimination, E1 reactions will always proceed to form the more substituted product, the more stable product. Similarly, because there is a carbocation intermediate and no geometric requirement for elimination, the reaction will proceed to form the more stable stereoisomer of the product. For example, the trans product if a 1,2 disubstituted alkene is formed. We'll end this lecture video with a concept check question. Which of the products below will be the major product formed from the E1 reaction shown? In this reaction, there are three possible reaction products: the terminal alkene and the internal cis and trans alkenes. Because I was told this is an E1 reaction, then I know it proceeds through a carbocation intermediate, and so it will form the most stable alkene product. The most stable alkene product that can form from this reaction is the internal trans alkene.